Thank you all for sticking around. And as I suppose, I hope, a reward for sticking around, I'm going to play a totally gratuitous video. And as preface to the video, that's not the video. As preface to the video, I have had the unique opportunity to do a fair amount of television shows over the years. And so this is from National Geographic, a television show probably about 2007 is I think when we did this. And the idea is this, I want to show you the whole thing. I thought it was gone from ever. I couldn't find it anywhere until I discovered YouTube has it. Haha. So it's from a program that National Geographic did called Known Universe. And this was a show called The Fastest. And the idea is, even if you travel pretty fast, it takes a long time to get anywhere on the scale of space and the galaxy and cosmos in general. So to try to illustrate that, I got involved. So here we go. Ready? Not that. Yeah, ready to vote. Hopefully we'll get sound. Do we get sound? How do we do this? I need sound. Plan ahead. Audio input PC, that is correct. PC, is PC going to play the sound? You shrink it, come back. One sec. Oh, there.
But it's still going to take New Horizons 9 years to get to Pluto. That's because the distances in our solar system are enormous. For a little perspective, take a fast car at a speed we can understand, like 100 miles per hour. Physics professor Lou Bloomfield will show us just how far that would get us, joyriding around the solar system.
Even in a fast car like this Lamborghini, it takes a while to get anywhere. If you were to drive across the United States at 100 miles an hour, it would still take you about 30 hours to complete the journey. Suppose you wanted to go to the moon. Now, you'd be traveling at 100 miles an hour for about 14 weeks. What if you went to Neptune? Neptune, the last planet. Well, you're talking about 3,100 years at 100 miles an hour. So if you'd started when Socrates was a kid, you'd still have maybe 500 or 600 years left. Long trip. That's because in this universe, the distances are truly enormous, and 100 miles an hour is nothing. You need something a lot faster. Like light. Nothing is faster than light. Yay! Why that fits into the story, who knows? But it was fun. Yeah, I got up, in this case, up to 130 miles an hour on a closed track, which is pretty fast. It was as fast as I could go around that corner. And the editors go crazy. Those of you who do media studies and stuff like that, the modern video and stuff, people have to edit the heck out of it. So it's flash, 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 flash. And the most interesting take we did was me going around the corner at 100, 130 miles an hour, coming to a stop, which you did see, me talking to the camera as the camera's walking around me, and then me peeling out all in one shot with a Steadicam. If you know what a Steadicam is, now here's physics, is if you can get the camera basically to be inertial, support it in such a way that the person carrying the camera can accelerate and stuff without the camera doing much acceleration, and particularly no angular acceleration. The Steadicam manages to pull this off, but it's hard work for the person working with it. And you've seen countless shots taken with Steadicams where you're walking along with somebody and they're going up staircases and all sorts of things. Like, how in the world do they manage to get the camera to do this? It's some poor person carrying this apparatus that it takes the acceleration out of the story. Anyway, it was a very elaborate shot. We did it in 2 takes. The first take, I talked to the camera, got everything done, and was going to peel out of there, still on the shot. And instead of getting the gear shift to go, it's got paddle shifters. If you've ever, the Lamborghini, it's a stick shift car in effect, but there's no stick down here, there are paddles. It's very cool. Except that if you miss the paddle and instead go for the windshield wiper, it ruins the shot. And that's what I did. So the first one, Okay, second one worked great. And they edited it out anyway. They couldn't stand to have one continuous shot. It was too much for them. So they had to chop it off. And when I finished talking to the camera and peel out of there, they have to do some flashy stuff, which ruined the shot anyway. So after doing this, which was done up in Reston, Virginia, we went up and visited again. There's a dealership up there. We visited again. This was with my wife and my son, who was 19 at that time. And they let him drive the car too, at 100 miles an hour through Reston, Virginia. And he said that, without checking his driver's license, he said that this was the high point of his life to that time, was roaring around Reston. Anything else with that? The fastest I've gone, though, in these television show things was with BMW going 170 miles an hour. That's really fast, and that's too fast for me. We did it a couple times, and I don't have to go there anymore. It's kind of amazing that a stock, this is a diesel BMW, also in 2007, that a car essentially unmodified can go 170 miles an hour. And this is why the German cars in the Autobahn, where there's essentially no speed limit, they can do that. And fine, they can enjoy it. It's a little too fast for me. Okay, so back to normal business here. Last time talking about clocks, let me finish off last piece of clock. I got pretty close to the end, but the idea with clocks is that if you want a good timekeeper for a clock, that you actually have physically in the clock, it's not somewhere else as it is on your cell phone, then you need some device that you can predictably get a rhythm out of it that is almost unchangeable in any context. It just beats a steady beat of a drum that just doesn't change at all. And our first key point about toward that key step toward that is you want to use a harmonic oscillator. And a harmonic oscillator, the definition of it is it's got a stable equilibrium, and the restoring influence that shows up when you leave that equilibrium is proportional to how far you leave it, the displacement. So it needs a spring-like restoring force. Pull it 1 unit away, you get 1 unit of force. 2 units away, you get 2 units of force from that. If you've got that, you've got a harmonic oscillator, and you get for free, as part of it being a harmonic oscillator, this reality that the period of oscillation, the time it takes to complete one cycle, is independent of how big that cycle is, the amplitude of it. So that's great. Among the world's got lots of almost perfect harmonic oscillators. It actually has some that are conceptually perfect. They show up everywhere, and we're going to take them from clocks in a minute into musical instruments. But to stick with clocks, the first one I dealt with was pendulums. A pendulum is not quite a perfect harmonic oscillator, but it's really close. And as long as you keep the amplitude of motion modest, don't go swinging it all the way up till the pendulum bob is horizontal relative to the pivot. Just keep it down small. It's almost a perfect harmonic oscillator. keeps nice time, not very portable. So what do? You go to a harmonic oscillator that is portable, and the classic one of these is the balance ring. It's a little wheel that rocks back and forth rotationally with a restoring force that comes from a spring. And those clocks could be quite accurate. They were the classic timekeepers of watches before the electronic revolution and carriage clocks and such. I'll also point out it remains a great book called Longitude, probably published 20 years ago maybe, that tells the story of a fellow named Harrison, who in the, boy, I should know what years, late 1600s, 1700s, somewhere in that range, solved the problem of longitude. What's the problem of longitude? So this is a digression, but it's worth knowing. Why did people care about very accurate clocks? It wasn't to know when to eat lunch. It was because in order to navigate and know where the heck you were on the Earth's surface, east to west, you needed help. That was tough. Knowing what latitude you're at on the surface of the Earth is fairly easy. There are tools with which you can look at the sun or look at the stars and moon and know how far north and south you are, sort of where you are relative to the poles. That's easy. What's hard is where you are east-west, because the Earth turns. And everybody gets an opportunity to see the same stars as long as they're on the same longitude, same latitude. As long as they're on the same latitude, they will see the same stars, same sun, but at different times during the day. As the Earth turns, a person who is exactly west of you by 100 miles will be exactly where you are in some number of minutes, because the Earth will have turned to bring them there. Okay, so knowing where you are east-west was really tough. There was no simple mechanism for doing this. We didn't have no GPS back then, sorry. So there were a couple of possibilities for how to figure out where you were east or west, and the one that finally worked and won was really knowing time very accurately. If you really knew when it is right now, you could figure out by looking at what stars or the sun are overhead and how they're arranged, you could figure out where you were east-west. And that was a big problem, not for people on land who obviously know where they are east-west, but people at sea. And so there were huge numbers of marine disasters where people were off in where they thought they were east-west and crashed on the rocks or whatever. So in order to know where they were east-west accurately enough, like within a mile, they needed to know time accurately enough to within seconds. And that's after a long sea voyage. And a sea voyage is not being very hospitable to anything mechanical. This is a big challenge to try to really know what time it is exactly after a month at sea. And Harrison finally solved it. It's a long nonfiction story of how he did it. He spent his whole life at this. And he ultimately won a prize. There was a longitude prize, an astronomical amount of money back in the day coming out of the British government or out of England. And he successfully met their requirements with his clock. They took something like 20 years to pay him, to properly pay him, and I only think they paid him half. So, naturally, when the prize was actually won, it was a problem to get paid. But to go back to the physics of the thing, he built a clock that was about this big. It was like a big pocket watch. The one that won, H4, his fourth attempt, was like a big pocket watch, and it was built on a balance ring. So the timekeeper inside that was doing the tick, tick, tick back and forth. But it was wonderfully compensated in ways for all sorts of the issues of real life, like for gravity, for one, to make sure gravity really doesn't have any effect on it. But another one that was important was temperature. So if you build some gadget that's supposed to be keeping time, as the room warms up, everything expands with temperature. mean, a topic that I haven't really talked about in class. It came up in the book, I will observe that most things get larger in every direction as they get hotter. And that comes about because of the thermal vibrations as the atoms and molecules are bumping against each other, jittering around in a solid or even a liquid or gas. But well, I'll stick with liquids and solid. As they bounce around, as they get hotter, they bounce more vigorously. And they, on average, spend more time farther away from each other about equilibrium than closer to each other about equilibrium. They're bouncing back and forth about equilibrium, but the forces aren't spring-like exactly. They're a little bit messed up, and the atoms, molecules spend more time on average apart from each other as they get hotter. So stuff gets bigger. This has influences in your life beyond just the clock problems. It's what breaks stuff if you move it very abruptly from hot to cold or cold to hot. Your kitchenware, glass, for example. You take a piece of glass that you have heated quite hot in the oven. It has gotten larger because of this effect. And you now run cold water into it and cool part of it. The part that you cool shrinks suddenly. And it fights the part that hasn't shrunk yet. And the two of them tear each other apart. So thermal expansion is just everywhere. And Harrison had to make a clock that, despite thermal expansion problems, kept a steady beat. And you can imagine as stuff gets bigger, the rotational mass increases. Got to deal with that. So he dealt with it, and he got a clock that was good to a few seconds after a sea voyage of many days, weeks, months. All right, so that was the technology of up until about 1960, 70 that most people would have available to them, ring balance clocks. And then you got quartz clocks, and that's where I'm going. So what a quartz clock uses, I'll say in a minute about the fact that it's using literally quartz, the crystal quartz, the same stuff that you see if you're, most sand is crystal and quartz. You might just find rocks kicking around that they're pretty much clear, and they typically have facets on them like they were cut gems. Not always, and sometimes they're kind of deformed or worn. But crystal and quartz tends to have this crystal structure to it that you can actually see on large scales, facets. Anyhow, the first issue is just solids can vibrate. And my example that, if I can try to get it going again, is just a piece of aluminum. And it can vibrate. Getting it started is always hard. So what I'm trying to get it to do is to vibrate so the ends go apart, the ends go together, back and forth, getting longer, shorter, longer, shorter, longer, shorter, bouncing about the middle. The middle stays put as the two ends go toward the middle and then away from the middle. It's not going to work for me today. What I need, this process that I'm trying to get going is a stick-slip effect. I want it to, my fingers to stick to this, pull it for a while, and then slip and let it go back. And pull it and slip. Now I'll cheat again. Can I get that? It's just too hard. We used to have a spray chemical that would really get it going on. Love to find that container again. But if I got it going, it would bounce. The two ends would go apart, together, bouncing about the middle. And that motion, it's very fast, obviously. It depends on the mass of the two ends and the stiffness of the middle. The stiffer the middle, the stronger the restoring forces, the faster things happen. The less mass on the ends, the easier they respond to the restoring force, and the faster everything goes. So making that rod shorter and stiffer and harder material will make it go faster and faster, assuming I could get it at all. By the time you get something about this big, it's going really fast. I mean, assuming you make it out of anything stiff as aluminum. And so it's now way past what you can hear Let me try a little water on my fingers. Maybe I can get that. I'm desperate. Yeah, just frustration. Anyhow, so if you get a little teeny piece, it's going to go like crazy, right? So instead of using a solid piece of material that is trying to go back and forth like this, what if you cut the middle out so there's not a lot left in there? You still get that same motion, but by taking most of the middle out, you've weakened the spring. The restoring force gets weaker. And that's what a tuning fork is. So a tuning fork, it's still a piece of aluminum, in this case. It's still got two ends, but the middle has been cut away, and so it's not as stiff. I can actually make them move toward each other or away from each other with my fingers. And instead of trying to get them going by playing with that, I give up. I can just whack the whole thing. Remember, you can invest the energy in some rhythmic system two different ways, right? Give it a hearty push, one whack, or the rhythmic pushes. I was trying to give it the rhythmic pushes over there, that bar with no success. Blah. Okay, so now it's doing that motion. I'll talk in a minute why it's so quiet. When it's doing that, you can't hear a lot, right? Unless I go up to the microphone. You hear that motion back and forth? You'll notice that even though this has got a lot of aluminum around it, it's going pretty slow. A lot slower than that bar would do. The pitch that I'm trying to get from this bar is this pitch. You hear it? Okay? The reason why the pitch is down so much is because even though I've got a fair amount of mass, I had fair amount of mass there too, but the restoring force is not very stiff. It's kind of mushy. All right? So, clocks. Quartz watches contain a tiny little tuning fork in them. Actually, they are preceded a little bit by metal tuning forks, but that didn't last long. Then they went to quartz tuning forks. So there's a tiny little quartz tuning fork hiding out inside every quartz watch or quartz clock. They make a tuning fork out of it rather than a solid chunk because the solid chunk goes too fast. It goes back and forth. Electronics actually can deal with that back and forth very fast. It's okay. But if you want to make something that's portable and lasts a long time, you want to make something that's energy efficient. And it turns out that very fast motion of a solid piece of quartz or metal, the very fast motion means you have to count very fast. If you want to count the ticks, you're counting 1, 2, 3, 4, 5, a million, 10 million, 20 million, 30 million. It's too much counting. The counting consumes electricity, electric power, energy. And so a clock or a watch that counts slowly enough that it doesn't keep the counter extra busy and consume electricity, and yet doesn't make noise is ideal. So they pick the quartz tuning forks that hide in all the watches that actually that are real watches, real quartz watches. They contain a tuning fork that vibrates fast enough that you can't hear it, although maybe dogs and cats might be able to, but slow enough that it doesn't wear out the battery fast. And it actually goes, it's a power of 2 is the one that everyone's settled on. Powers of 2, 2, 4, 6, 2, 4, 8, 16, 32, 64. These powers of 2, it makes it very easy to count. And so they run at 35,000, I forget the exact number. It runs around 35,000 cycles per second. It's 2 to the 15th, I think. And that's what's going on inside a quartz watch. So it's actually taking place in I do have a real quartz watch, no radio connection to the internet and stuff. and it's whizzing away, and they're doing that. Why quartz? Quartz for a couple reasons. One is quartz, among ordinary materials, it has one of the weakest responses to temperature. So if you change the temperature of a piece of quartz, it doesn't expand very much. Everything else expands more. Quartz is pretty much, it's sort of the lowest expansion coefficient of most things you'll encounter. So that means that your watch will run the same on your wrist as it does on the bedside. Where, on your wrist it's warmed up by you. On the bedside it's whatever the room temperature is. That's actually an issue. That change in temperature is a problem for some clocks. Quartz clocks can deal with it because they just don't respond much. The other thing about quartz that's kind of cool is that it is a piezoelectric material. And what piezoelectric means is that there is a relationship between its mechanical stresses, what you do to it, pushing on it, bending it, and so on, and its electrical properties. As you push it around and stuff, for example, it moves electric charge around. And as you move electric charge around it changes its shape. They're connected. And you're familiar with things that have that connection. The spark starters in so many gadgets. Do I have one up here? Nah, you never know. The things where the grills or a gas stove where you push a button or something and it smacks a crystal. It's smacking a piezoelectric crystal. It could be quartz. And that mechanical shock ends up as an electrical shock. They're connected, okay? So what the quartz tuning forks in a watch or clock do is the clock niggles them with an electric effect and gets them vibrating. And once they're vibrating, they develop their own electrical effect that comes back to the clock. So the clock is basically interacting with the quartz crystal electrically, and the quartz crystal is there vibrating. It's a little tuning fork. It's really doing that mechanical vibration. It's very small, and it's very fast, so you wouldn't see it. But it's there, and it's doing it. And the last thing I'll say about it is that making a whole slew of these little tiny tuning forks, and I have them downstairs and didn't bring them up, the little itty-bitty tuning forks, it's hard to make them all vibrate at exactly the right frequency, just right off the shelf. Like you just make it and hope that it's exactly in tune. It won't be. They tune them. They tune every one. And how they tune it is they put extra metal on its surface, because the metal is part of the electrical interaction with the quartz. And then they get it vibrating, and then they remove metal until it vibrates at the right frequency. And they remove metal with a laser. They just burn away the metal until it comes into tune, and it's done, and they ship it, put it in a clock, put it in a watch. All right? So it fulfills the usual requirements of a clock. There is the timekeeper, which is the little tuning fork. There is the energy source, which is now is a battery. And the battery's job with the electronics is to keep shaking the quartz a little bit. It adds a little energy to the quartz every cycle. And finally, there's a counter that just counts the vibrations and advances the count, telling you what time it is now. That's the whole story behind a quartz clock. Any questions about clocks? Okay, so on to musical instruments, which is more the same. The difference between a quartz clock, a clock and a musical instrument is, musical instrument is again, almost all of them are built around harmonic oscillators, but they're harmonic oscillators that have more variety to them. And quartz clock's got, a clock has only one rhythm. It only knows one note, one musical note. And it just keeps doing that all day, every day. Musical instruments have a lot more flexibility. And part of that comes about because their harmonic oscillators, instead of being a single object with a single inertia and a single restoring force, they're complex objects, like strings or pipes, or the air in pipes. And those complex objects, which they're extended objects, they have a length to them. They have at least one dimension. Actually, one dimension looks good. 2 dimensions is problematic. 1 dimension, the length of the string, along the string, along the pipe. you can get multiple harmonic oscillators out of the same object. And that may sound mysterious, but I'll show you what I mean by that. So I've got a string up here going from left to right. You know, it's about, what, 10 feet long, 3 meters long. And it's under some tension. And the tension is necessary because it gives that string an equilibrium shape. The string wants to be straight, right? We'll leave gravity out of it. Gravity's a nuisance here, and it doesn't add anything important. We can just sort of pretend it's not there. With the tension present in that string, it wants to be straight. And if we pull it away from straight, restoring forces show up and pull it back. And the restoring forces, you know, if I distort it over here, there's a restoring force here. If I distort it there, get different restoring forces. You know, obviously, I pull it away, you know, it goes back. But you're seeing now, if I pull it away and let go, it bounces back and forth about equilibrium. That's all familiar territory. It accelerates back toward equilibrium because it's a stable equilibrium. It overshoots because of inertia and momentum, and it goes up and back. But different parts can go in. We can get all kinds of complicated movements. This is one of these cases where I can distort it part above, part below. It's really complicated how the shape that I can get it to go into, and each one gets restoring forces. How do we ever figure out how to describe the motion of this thing? Because it's too complicated. It turns out that this thing simplifies if you think in terms of arcs, just simple arcs. And they happen to be trigonometric. They're you know, sine shapes and cosine shapes, things you remember from back in the day somewhere. If we work only with limited shapes that the string can have, it turns out that each of the shapes, if we pick the right shapes, behaves as a harmonic oscillator. And to show you what I mean, let me get one of these guys going. So there's a flash lamp up here, which may or may not be valuable. We'll see whether this is helpful. Let me get the... Can I go more? Right now, it's pretty much bouncing up and down as a single arc. The arc is going up through the middle, down through the middle, up. It's going back and forth about a straight equilibrium, up and down. We have two ways of driving this string historically, you know, here in the department. One is a electromechanical, a motor that shakes it violently but is uncontrollable and drives me nuts. So I rejected that. This is an electromechanical shaker now that we can control very carefully, but it's not quite as aggressive in shaking that guy. So it's not going up and down as violently as would be ideal. So I hope you can see the arc. It actually is a trigonometric sine function. It starts from 0 here, it goes to a peak in the middle, and then it goes to 0 at the end. That arc, you know, to describe the whole thing, where do I start? This is what's known as the fundamental vibrational mode of a string. So it's a string under tension. This is the simplest way the thing can vibrate and not violate laws of motion and stuff like that. It's one smooth arc that goes from 0 to 0 in amplitude at the ends and maximum in the middle. And just to give things names, there are official names for some of these features. The place of peak motion, which is right around here, is called, oddly enough, it's called an anti-node. What's a node? A node is these places here at the end that basically don't move. That end's a true node. This one's approximately a node. And so this fundamental vibrational mode has two nodes, one at each end, and an antinode in the middle. And that's the simplest way this string can vibrate. This is the vibration of a jump rope. Have you ever played jump rope? Do people still do jump rope? I hope so. You might be going around in a circle rather than straight up and down, but it's the same motion and the same physics. And it has one antinode and two nodes at the end. And incidentally, this is also the slowest vibration this string can have. So if this were going faster, you would begin to hear it. It would develop a pitch that you would sense as a musical note. And this would be the lowest note that this string can produce. This same string, however, can produce other notes, and it can vibrate in different ways. And this, just to give you a piece of information here, this vibration is occurring at 4.4 hertz. What's a hertz? That's a cycle per second, a measure of frequency. So the frequency, that is the number of cycles it's doing per second, called a hertz, cycles per second, is 4.4. If I go to 8.8, twice the frequency, I should get another vibrational mode. This is called the fundamental vibrational mode, where mode, it says, this is a way that the system can vibrate in its most basic structure. So this is the simplest of those vibrational structures or modes. If I go faster, so then I'm going to go up in frequency to 8.8. I should be right about here. Here it is. I'm wheedling around looking for it. Oops, overshot. There it is. Okay. It's occurring at, well, 9.4. It should be 8.8, but it's a little bit off. I might have been a little off on the fundamental. This is called the second harmonic mode. There is no first harmonic mode. First harmonic is the fundamental. So this is a mode that occurs in a string where it vibrates as two half strings. It has another node. Right there is a node, vibrational node. It's where it's not moving. And now it has two antinodes, a maximum here, which is an antinode, and a maximum motion here, which is an antinode. So in this mode of vibration, the string has three nodes and two antinodes. It's now it's asymmetric in that the left side goes up when the right side goes down and vice versa. What else about it? And it occurs at in principle, twice the frequency, exactly twice the frequency of the fundamental. And I'll come back to that particular behavior. So when you play with a string, the string of a guitar, the string of a piano, harp, any of those, these kind of motions are taking place on it. When you pluck a guitar string, the strongest way in which it's vibrating is its fundamental, but it also has some of this in it, some of this second harmonic. And if I go up to 3 times the fundamental frequency, I should get the third harmonic. So 4.4 is about 13. I should be up here. There it is. Okay, 3 1/3 strings. And I added a node and an antinode. And it's occurring at 3 times the fundamental frequency. And if I go to 4, where is it? It was there. I can't tell what that one is. Oh, there we go. 1, 2, 3. This is the fourth harmonic. We'll go for fifth. There's the fifth harmonic. Okay. Sixth. Okay. So what I want to do is, does a straw have 1 or 2? A straw is a musical. We'll come soon to air in pipes, and air in pipes, amazingly enough, can do the same sort of thing. But instead of the motions, these up and down motions for a horizontal string, in a pipe, the air has to move along the pipe. So the motion is in the same direction as the extent of the air. Here, the motion is at right angles to the extent of the string. In a pipe, it's along the string. And so the motion involves regions of high density and regions of low density, up and down, back, as the air bounces back and forth in a straw, for example. There are fluctuations in density, whereas here there are fluctuations in distance away from the equilibrium center. Anyway, a straw is open at both ends, and so it behaves like a pipe that's open at both ends, which is most wind instruments, flutes, organ pipes. They're open at both ends of the pipe. The openings may look different. Like in a flute, one is a little mouth hole, and the other is at the end of a pipe, but it's open at both ends anyway. All right, so what do I want you to take away from this little story? I'll stop this guy from vibrating. Oops, I want to go to the stage. There we go. When you're playing any stringed instrument and you get the string moving, it vibrates basically in a mixture of those basic modes. And whatever shape the string ultimately has at one instant of time is constructed out of the individual mode vibrations. They add together, they can sort of live together on the string. And they can create very complicated shapes by adding together an arc that's up, one arc that's up and half down that can decide both of those two, I'll make this too complicated. But you can make very complicated shapes in the string by adding together these basic modes of vibration. And so when you pluck the string of a guitar or bow the string of a violin, you get these multiple modes going at once. And each one has its own frequency, the frequencies being multiples, integer multiples of the fundamental frequency. How to make this so it's followable. The fundamental frequency of a string has a specific value. Where's the string? Here. If I pluck this string, do you hear that pitch? That's the fundamental pitch, where the string is going up and down as a single arc. But superposed on that is a little bit of the second harmonic, where one half of the string is going up as the other half is going down, and the middle staying put. Can I get that going? Can I cheat and touch the center? Not really, but it's present. Getting it going to the point where you can hear it is tricky. Same with the third harmonic, where it's vibrating as 3 1/3 length strings going up, is also going to be present. They're all going to be present at once, and the mixture of those three things being present, which you can hear, I mean, you hear the fundamental mostly, but the other ones actually are present and your ear catches them. You interpret that, you identify the instrument based on that in part. You listen and you go, oh, there's actually some second harmonic and third harmonic there going on in that. So I know that this is a stringed instrument. As opposed to what? Well, for example, a flute, which we'll see has a vibration. It's got a fundamental mode. It's got second, third, fourth harmonics and stuff. In a flute, it's almost pure fundamental. So a flute has a very clean sound that has very little of the other sounds present associated with the other modes of vibration of the air column. I need to go somewhere with this. Okay. Where I go, I'm leaving a lot of odds and ends undone. Let me go to this, since we've gone to the trouble, Al's gone to the trouble of setting up that glass over there. Here's the story that I'm going to follow right now, is that so many objects that are, as long as they are extended objects, that is, they're objects that have at least one dimension along which the material extends, and they can vibrate, all the little pieces can vibrate. They all end up having multiple modes of vibration, and as long as they've got a stable equilibrium and good restoring forces, they'll vibrate about that stable equilibrium in various basic motions. A wine glass fits the bill. It's got a stable equilibrium, namely this shape. And if you take it away from this shape by squeezing it or stretching it, it vibrates back and forth about this shape. Its fundamental vibrational mode, if we look down on it, which we're doing over there on that, the other projector, we're looking down on a wine glass like this. It happens to be that one over there. The vibrational mode that's most basic is for it to go oval. So it's circular normally, that's equilibrium. It goes oval first, say horizontally, and then vertically, back and forth. This is the motion that it does in its fundamental vibrational mode. And I can get that going two ways. I can just tap it. There it is. That's its fundamental vibrational mode. And it's doing the oval trick back and forth. Okay. That's one way. The other way that you can do if you're bored at a fancy restaurant, if you're like me when I was a kid, this was standard operating procedure here. Come on. This guy's vibrating under, I'm getting other. This is the equivalent of bowing a violin. My fingers grabbing the glass, pulling it, and then letting it slip away. And that's happening hundreds of times a second. And so I'm bowing the glass. Okay? It's the same tone as this. So you can get that motion going either by smacking it or by rhythmically doing work on it every cycle, which is what I was doing with my finger. Another way to do rhythmic work on it every cycle is to simply sing at it. And Caruso could apparently do this. It's hard to do. If you sing at the wine glass at its favorite frequency, the one it will emit when you bow it with your finger or when you smack it, you can get the motion going. And as that motion gets stronger and stronger, the physical shape goes more and more out of whack until eventually it exceeds the structural integrity of the glass and the glass breaks. So that's the plan here. Let me show you. The time is good. I'll do it here. So what I'm going to do, you're with that projector, you're seeing this camera here, right? The camera's looking down at the glass. There's a strobe here that should illuminate it once per cycle so that you can see it get out of round. Otherwise, it just looks blurry. And it will go out of round, and eventually it will break. And what's hard to predict is how loud the sound has to be before it breaks. But this is the real story of breaking glass with sound. You want to pick the natural resonance of the glass, not any old sound. It's not just somebody shrieking. No, that doesn't break glass. You pick the sound that the glass makes in its fundamental mode, and you sing at it at that pitch really loud. And you get its motion going to the point where it breaks. And you can see it going out of round. This is normal. This is out of round. Ready? I may have to adjust the frequency a little bit. There we go. So a little bit of a hodgepodge day, but I'll tidy it up on next Monday. Have a good Thanksgiving break and all that. Thanks again for coming, and see you. Bye-bye.